Thanks, Brigitte, for the invitation. It's wonderful to be here and talk about this new framework. So this will be the third sort of time some content like this has been presented to a Berkeley audience, so I won't be offended if you get up and leave now. But I'll try to give a little bit. It's a different. I'll try to give the less TCS version. So a TCS version of this has been given actually here by Robbie, who's listed right here. And then there was a math version given over in the math department. But since this is connected to the chemistry conference, I'll sort of try to give a chemistry perspective on some of these things. OK. So what I'm going to talk about is SOSA. It's a new algorithmic framework, and it combines two things that are already developed ideas themselves. One is sum of squares representations of Hamiltonians. OK, so maybe the quantum chemistry community isn't exactly aware of these things that much, but definitely in computer science they know about this and all the relaxations associated with it. And then a notion of spectral amplification, which goes all the way back to adiabatic quantum computing in 2013 with Sergio Bourgeois and Rolando Soma. It targets low energy problems. So if you're doing phase estimation on a low energy state, so estimating ground states, time evolution in a low energy sector, expectation value estimation if you have a low energy initial states, and thermal states if they're sufficiently low energy. And I'll talk about what low energy means in this context. It's really maybe not with respect to a temperature that maybe you're familiar with, but it's really respect to the representation of the problem with respect to this quantity lambda. And then, of course, at the end, we wouldn't be talking about this if it wasn't interesting. We can have asymptotic improvements, so complexity improvements, and then also constant factors. We compile all of these algorithms down to gates, and then we do see very large speedups for ground state energy estimation for chemistry and material simulation. I'll talk a little bit about that, which is some new content. OK, so what's the ingredients for this new framework? Traditionally, you're given access to a Hamiltonian, and you want to ask some questions about it. You're going to do time evolution, expectation value estimation, and whatnot. And a traditional method, as of, I guess, maybe 2016, is a block encoding access to this Hamiltonian. And this is given to you as a unitary, where you're putting that Hamiltonian that's been rescaled up into some corner, a block of this unitary. And so you can derive all sorts of simulation frameworks that access this particular unitary. You can do phase estimation based on this. That's the way a lot of the modern techniques work. There's time evolution. There's eigenvalue transforms. They all work on a block encoding query model. What we're going to demand for the spectral amplification framework is two more things. One is that we're given a positive Hamiltonian. OK, so I'll tell you that that's actually not that big a deal, though it does seem like a restriction right now. And we're given a block encoding of its square root. So just if you're given a Hamiltonian that's positive semi-definite, let's say it's written down as a quadratic function of operators, a dagger a, you're given access to a block encoding, a unitary of the square root of that a. And so I'm talking about this in very sort of vague generalities, but this is just to sort of paint this picture of how this framework gives you a speed up in a lot of different scenarios. OK, so to be a little bit more precise, we can imagine if we're given access to this block encoding of the square root, we can actually perform this spectral amplification Hamiltonian here, which is formation in this case. And this thing will square, at least in terms of a block of your Hamiltonian, to your Hamiltonian itself. And the eigenvalues of this spectral amplifiable thing are the square roots of your original Hamiltonian, namely singular values, once you appropriately rescale by the normalization factor, the block encoding normalization factor. So let's see what happens, actually, if you're given access to square roots of things. This is not a very complicated notion. If you have your spectrum that's between 0 and 1 of a positive thing, right, you take the square root of that, all your levels are going to spread out, right? So we're going to use this to our advantage, the fact that they're spread out a bit more, but we'll be able to obtain dynamics effectively faster. OK, so let's do a little bit of a toy problem related to this. Let's say that you're given access to the square root of x as a random variable, and you want to estimate x the dependent variable in this case, to constant precision. And I'm not going to tell you where you are on this curve, but imagine there's a bunch of different scenarios, and there's different estimation tasks that you have. Well, you can actually just square your estimate and determine exactly the error that you need to measure the square root random variable to get constant precision x here. And that's going to be this constant precision epsilon. And so this graph shows you what's going on. All of these red bars are exactly the same epsilon, right? That's my goal, right? And we notice that the precision that I need to measure the square root to is getting bigger, or is getting looser as I go towards 0. Okay, so this is sort of a basic fact of uncertainty propagation. For the chemists in the room, you might remember from general chemistry, you're given a function, and you have to propagate the errors correctly by first Taylor expanding, and then inverting the first order of that Taylor expansion. This is doing exactly the same thing. Okay, and so we can use this uncertainty propagation to our benefit. If we are in this low energy sector, effectively we can measure something with much higher uncertainty. So in quantum computing, this usually means fewer resources to get the same precision if we're in this low energy regime, or in this case, close to 0. Okay, so let's see how this fleshes out in a familiar setting. Let's say we're working with phase estimation. This is just textbook phase estimation, so there's nothing complicated going on here. But we're going to use our spectral amplifiable Hamiltonian to build our unitary. I'm not going to tell you how to do that, but let's just say we can, right? And we're given a low energy state. This is part of the input to phase estimation, right? What we're going to estimate now is the square root of the energies rescaled by lambda, right, to some fixed precision based on the number of bits in my phase estimation. And then we can just recover the eigenvalues by squaring. And again, this is the same picture as we saw before. If our precision estimate, if we're given a low energy state, our precision estimate is becoming larger as we approach the low energy sector for this particular task. So this might look a little bit weird. My energy that I'm estimating is actually in the precision here, and so I'm making some type of circular argument. But I'm going to bound this quantity for low energy states given a non-negative Hamiltonian, so something like this. And so this is sort of painting the picture of how you actually can use this uncertainty propagation if you're given access to the square root representation of some Hamiltonian. So that's it. That's like the entire spectrum amplifiable sort of framework. What you can do is then build all sorts of quantum algorithms that leverage this idea. So expectation value estimation is actually just phase estimation on a 1-by-1 block, right? So that's just generally how that works. Or amplitude amplification is effectively phase estimation on a 1-by-1 block. So all of this carries through, right? The same math, except instead of a big state, you're given your initial state. This works for time evolution in a low energy sector. There, if you're using signal processing to produce the dynamics of the for the time evolution, you effectively need a lower order degree polynomial approximation to the cosine theta and sine theta if you're given access to the square root. So that's how that speed up there shows up. And then all sorts of things. So you can effectively build lots of quantum algorithms based on this idea. Okay, so there's a nice sort of translation table that you can make. If you're given access to this, if you have these two extra ingredients, right, and you're building a method that's based off of QSP or QSVT, which you can massage a lot of quantum algorithms into, then you effectively take the costs, the query complexity costs of block encoding, like lambda over epsilon, and that gets translated to square root of lambda times this quantity delta, which is effectively quantifying how low energy you are in this problem. And so there's actually a handful of papers that we went through and just specified the algorithms for each of these. And this is actually optimal query complexity for time evolution in this particular access model. Okay, so that's pretty nice. This is all sort of a consequence of this uncertainty propagation and the fact that you can obtain dynamics a little bit faster when you're given access to this square root. Remember, you're in this regime 0 to 1, and so things spread out. Okay, so why don't we do this all the time? That's sort of the question. Well, you needed these two extra ingredients, right? And they seem pretty restrictive. You needed a non-negative Hamiltonian, and I need to block encode its square root, right? So for the chemists or other, condensed matter simulation people, you've probably never been handed a Hamiltonian that's given to you as A dagger A, unless maybe you work in error correcting codes and they're like defined by stable like projectors, right? But most of the time we don't see Hamiltonians like this. And so let's try to build one of these sum of squares representations that's a non-negative representation of a Hamiltonian. So we can start with something that we do see pretty often. Let's just define our Hamiltonian as a linear combination over polys, right? Polys are going to be sigma of some size, like maybe they're all k local or whatever, right? And we can convert this into a sum over projectors. That's the second line here. Because polys are Hermitian unitary, we can just perform this transformation, and we can then rewrite our Hamiltonian such that it's the square root plus some shift, right? And our shift is coming from this fact that we have to shift all of the polys by some amount, right? Okay, so what we've done here is that we've just rewritten our Hamiltonian plus some shift is equal to some non-negative representation, right? What I've done is I've dilated my problem. I've made a huge rectangular matrix where I've put every projector into a different row of this big rectangular matrix, and then I can square that thing and I get back my Hamiltonian plus a shift. That shift now is exactly how much I need to shift each of my operators by to make this thing non-negative. Okay, so what happens now? Well, let's remember our SOSA framework. It's now going by the gap of some non-negative Hamiltonian, which is going to be this guy here, this sum of squares thing. But that's actually related to our original Hamiltonian plus some shift, right? And so we need to see how much we've shifted this with respect to the energy that we're trying to estimate, this E0, right? So because we're shifting by the entire block encoding 1 norm, it shifts it by a very, very large amount. So we've pushed all of the states up into an extremely high energy sector. And there's no states now in this low energy sector that we can actually benefit from spectral amplification. Okay, so this was actually a way to generate a bad sum of squares representation. Okay, so this is just telling you why we can't do this super generically. But there is a solution to this, it turns out. Okay, so why doesn't that show up? Great. Okay, so the way to generate a good SOS has actually been around for a really long time. We can borrow ideas from computer science. It turns out in 2000, it was just generically proven for Hamiltonians written in non-commutative algebra, you can always write a non-negative representation of that as a sum of squares. That actually is different from the classical case. If you're given some polynomial over some variables, you can't always write it as a sum of squares representation. But we can do this always for some Hamiltonian written in a non-commutative algebra, so like ladder operators, poly operators, whatnot, right? And we can then sort of design a computational procedure where we try to figure out the most optimal representation of some non-negative representation of that Hamiltonian with the best lower bound, so the tightest shift, the tightest shift to the ground state energy. So in computer science, there's this whole hierarchy of approximations that you can keep increasing the many-body order of your sum of squares ansatz, and this gives you a tighter and tighter lower bound. I won't go too much into detail about that. What's important to know from the chemistry side is this is exactly the dual representation of V2-RDM theory. In fact, you derive all of these n-representability constraints actually starting from this picture. And so there's a very nice and clean connection to this. We wrote a whole separate paper on fleshing that out specifically. But remember, our goal is to write down a representation of our Hamiltonian that's a sum of squares with a very good shift, so that the delta here, this delta, sorry, I should have called this delta, not ESOS, is small, so that when we dot it with our new block encoding lambda, this whole quantity is as small as possible. Now, there's a trade-off, of course, right? This tells you that you can always pay more to have a tighter and tighter representation of the lower bound or the ground state energy of your Hamiltonian by increasing the complexity of this particular operator, this sum of squares, right? But our total costs for our algorithms really depend on the cost of implementing this square root, namely all of these O alphas. Times the query to the block encodings. And so that's going by this guy times the cost, this guy. So we want to optimize both of these quantities at the same time, and that's the game that we can play. So it's not a free lunch. You can't just make the gap super, super tight, and then all my quantum algorithms will be faster. You do have to play this game, and playing this game correctly is the challenge. The goal is, of course, to find a near frustration-free representation of the Hamiltonian. And so what do I mean? This is some non-negative quantity because this is a lower bound to the ground state energy, right? So you can think of the left-hand side as just the Schrodinger equation. And then the right-hand side here, each of these, if the lower bound, let's say, is the ground state energy, the expectation value, if you're given an eigenstate, of course, the ground state is going to be 0. So we can't, of course, make this perfectly tight. And so all of these expectation values, if you're giving the ground state energy, are very close to 0. They're very, very small, right? And so that's what I mean by near frustration-free, the computer science sense. OK. So let's do, when I've presented this before to quantum chemists, it's sort of a mystery or very exotic looking that you can write down a Hamiltonian this way. So we're going to do a very basic example that hopefully paints this picture and paints the optimization problem that we have to do, and then I'll give an analytical solution to it. OK, so let's say you're given a Hamiltonian that's a quadratic of fermionic ladder operators. I've written a diagonal form, but of course you can just similarity transform each of these operators into any basis and make it non-diagonal. But it's simplest to work on the diagonal form, right? So I'm going to work at the SOSK level 1. Namely, my SOS generators are in the span of just the single ladder operator algebra. So every operator O is going to be some linear combination of each of these operators here. Okay. Now I can set up a SDP where I'm going to try to maximize my lower bound. Here's my lower bound here, right? This is the equation we had before. But I need to maintain this equality. I need to maintain that my Hamiltonian minus this shift is equal to my sum of squares representation. That's the linear constraint that goes into this. Now I'm overloading a bunch of the representation here, right? Like these are actually just, this is a Gram matrix, and these are all normal ordered such that it equals my Hamiltonian. But maybe we can work out those details later. And this Gram matrix must be positive semi-definite. So this is an SDP that you have to solve. But of course, for quadratic Hamiltonians, we can identify an analytical solution to this right away. We know if you're in the bound state sector, right, your VJs, or your state energies, are going to be negative. And so you can actually just employ the commutation relations, anti-commutation relations for the fermions and reorder them, and you pick up this constant term. And that gives you exactly a sum of squares representation of this quadratic operator. See? This is a sum of squares, so A dagger A. This is also a sum of squares, A dagger, right? Or Hermitian sum of squares, I should say. And this gives you the SOS representation of this quadratic Hamiltonian up to this constant shift. And it turns out for this problem, this is exactly the ground state of that Hamiltonian. You can do this in any particle sector you want. You can actually add Lagrange multiplier terms. There's a very complicated theory about how to do that, but you can effectively recover all of RDM theory based on this. And so this is how you would extend. This is sort of the general setup of how you take a Hamiltonian that maybe you see in quantum chemistry or condensed matter and then turn this into an SOS. You solve one of these semi-definite programs, either analytically or computationally. OK. I put this in here because I wanted to point out that once you're given this SOS representation, it's effectively giving you a low variance representation of your Hamiltonian. So if you're in the ground state, it's effectively telling you H minus your lower bound. If that's tight, right, then each of these operators, these sum of squares operators, have a small expectation value, right? That's the near frustration-free representation benefit. So there's actually a bound that you can write down for the variance, and if you're going to perform tomography on this thing, it's called the Bhatia-Davis bound. It uses just this information that you are close to one of the sample limits, so the ground state effectively for each of the terms, and that gives you a tighter variance for tomography. And so all these graphs here are just showing you what happens if you take an Ising Hamiltonian and you write it as a sum of squares, and you compare that to sort of a naive estimate where you're measuring all of the x terms and all of the z terms. And so you can see from the green and yellow, if all of these are based on the variances of some initial state that I just guessed, and effectively that's telling you how expensive it's going to be to measure the energy. And so this is a property of being in this near frustration-free representation, in the same way that in the quantum computing case or the quantum algorithms case, we're using this near frustration-free representation to obtain dynamics faster and then get faster quantum algorithms. OK, great. So what does this look like for something that's maybe near and dear to our hearts, the chemistry electronic structure Hamiltonian? I've moved the one-body term into the two-body term case just for simplicity of representation. And we can ask ourselves, what is the simplest algebra that we can use to represent the electronic structure Hamiltonian? And I'm going for the simplest thing here, because remember, the cost of my quantum algorithms is going to be proportional to the block encoding cost of the square root, all of these b's. And so I want something that's pretty cheap, but still gives me a good gap. And so the simplest algebra that we can use is the unitary group generators, or the spin-free sum generators. EIJ is what we usually call them. And that's sort of depicted here, where I'm representing each of my polynomial, or each of my SOS generator polynomials B as a linear combination over single ladder operators, and then over a spin sum ladder operator here with a particular coefficient. OK, so this is a fairly small semi-definite program. It's about the size of your Hamiltonian, assuming the correct symmetries and everything. And so it's not that expensive as a pre-processing step. And I think that's an important component of all these. You can't shove an NP-hard problem into pre-processing to make your life easier. And so here, the question is, does this give a good enough gap such that you actually get a speed up for interesting chemistry problems? And that actually turns out to be the case. You can solve this semi-definite program. You can get this lower bound energy estimate, that's E SOSA, for a whole host of interesting systems here. You can get an upper bound from any variational wave function you like. And then you can look at the effective lambda. That's the square root, again, of your delta in the energy. So namely, how far you actually had to shift up your eigenstates, right? You want that to be pretty small. Times the lambda associated with actually implementing one of these square roots. And so that's actually just given right here. And you can compare them. They're all actually very, very small compared to the simulation of these with respect to an LCU method. So that's actually a nice verification that even the simplest form of the sum of squares, which gives a tractable pre-processing step, can give you a nice improvement in terms of the queries to this square root block encoding that you would need with respect to the traditional method. And I think the important thing to point out is that these lower bound energies, right? These are the energies you get from solving the semi-definite program over the spin-free algebra, are off by like a Hartree. They're order 1 Hartree off. So that's terrible for actually doing chemistry, for thermochemistry, right? That's 4 to 8 times a hydrogen energy. But it's OK for this setup because we're satisfying this inequality. All we're doing is we're trying to find a Hamiltonian representation that is near frustration-free enough. And in this case, that works out. So there's probably lots of things in classical electronic structure that you could employ to do this. In fact, Matt Hastings has this nice conjecture that this extends to AFQMC. AFQMC, the sign problem is coming up from this competition between the two terms in your Hamiltonian, one body and two body. And then if you're rewriting this, then hopefully that's minimizing this competition in this near frustration-free representation. Of course, the devil's in the details there because like shifting works in AFQMC, and so you have to sort of see if this actually gives you a nice speed up for free projection. OK, so that's just what I wanted to comment on there. For chemistry, we can find these near frustration-free representations that give you a low enough gap such that it's a faithful representation of our Hamiltonian, and it gives us a speed up for quantum chemistry. And so Ivan put this up luckily earlier, so I don't have to explain it too much. But what this lets us do is it layers on a couple of algorithmic tricks that have been developed over these years. This is like factorizations of the Hamiltonian, so importing all of the knowledge of electronic structure in terms of efficient representations. This era is symmetry shifting, so shifting by some known symmetries like particle number, and that lowers your block encoding lambda a bit more. And then SOSA, we can push this down even further, and these are all layered on top of each other. And so the table on the right is the just factor of improvement in terms of the gate cost that we get over the traditional methods. So that's nice. This is sort of stackable and also sort of gives us a new avenue to optimize things more. Like this was the first thing that we tried. I think there's actually a lot of SOS that you can develop. You're not necessarily required to have this sort of CI-like description. Remember, each of the SOS generators are annihilating your ground state. So you can have all sorts of operators or structures that annihilate your ground state, and it gives you a huge design space. And so this is maybe a call to action that people can work on that. You can even use some tensor network things to do that. OK. Before I close, this trick does not always require you to solve a semi-definite program. That might seem like a pretty onerous pre-processing step. Maybe you don't have access to a fast semi-definite program solver. Maybe you're not good at doing all of this algebra and setting up this big computational procedure. But like I showed you for the quadratic Hamiltonian case, you can occasionally analytically solve this SOS equation to find a representation of your Hamiltonian. And lots of people are doing this for all sorts of different things. Lynn's here. He's used this trick in a variety of contexts. But in this case, it turns out you can also employ this to first quantized representations. And so for SOS, the whole game is trying to balance a representation that is block encodable cheaply, but also somehow captures the frustration in the problem, right? Now, it's not obvious that this is easily extended to lattice models. And this is sort of our first shot at this. You can think of a first quantized representation lattice model-like. And it turns out you can actually write a very cheap frustration-free representation, or near frustration-free representation of the Hamiltonian that gives a very similar block encoding cost to the original LCU method here. So what's the trick? There's actually lots of ways to turn a quantum or electronic structure Hamiltonian for a material or described in first quantization here into a sum of squares. Let's say one way to do this would be actually to group all of the potential terms together, and that's actually what we did. In fact, the way that we do that grouping is that we're looking at the electron charge density minus the nuclear charge density. That's the thing that's our SOS generator. But there's other ways to do this. You could actually turn everything into a hydrogenetic or hydrogen-like atom. This is the strategy that Lieb took in his stability of matter paper. There's a little bit of a bosonic collapse there, and so your lower bound is actually not as good. But it turns out if you select the correct SOS, and that's like part of the research of this project, is that you can prove a asymptotic speedup for first quantized simulation, going from what is here on the left, this is the query complexity, to the block encoding, to what is over here on the right. So we have a square root improvement in delta for one of the terms. This is the kinetic energy term. And then this is the potential terms. We have a square root improvement for eta, the electrons here. And so this is an asymptotic improvement. So as the system size gets bigger, this speed up gets bigger. So that's pretty nice. This was the second time we were able to prove a speed up for something like this. I'm not sure if this extends to like lattice models like K-local Hamiltonians or Hubbard. That's something that's pretty interesting to think about and work on. So let me know if you're interested. OK, so just to quickly demonstrate, this isn't really a compilation audience, so I'm not going to like belabor all of the details of how to compile these algorithms, but needless to say, that is an activity that we like to do at Google. But so if you do that and you look out in the literature at everything that's been simulated in first quantization in this representation, you can just, like I showed on the SOSA side, have a sort of translation table from regular LCU representation over to SOSA, and that's what we have here. This column is important. This compares the walk operator cost, that's the thing you're phase estimating, to the walk operator cost in SOSA, and they're actually very similar, you can see, all through here, right? And then the lambda is the thing that we really care about. Here's the LCU lambda for first quantized methods, and then here's what is employed for SOSA, and this is a substantial lowering. In fact, the speedups that we give are listed over here. And so, yeah, this is a sort of detailed work. You have to compile all of these to check that the block encoding is similar to what you had before if you're given access to this square root, and then see if the lower bound is good enough. But in this case, it works out and gives a pretty big speed up for simulating materials. Yeah, so what's next is, of course, doing pseudopotentials, because that's not in this, and that's the thing that makes these useful. The nice thing about a lot of pseudopotentials is they're actually represented as projectors already. So like the HGH pseudopotentials are represented as spherical harmonic projectors. So you can exactly shoehorn that procedure that I showed earlier in. And we're going to keep turning the crank on some of these things. OK, happy to take any questions. Thank you.
Of course. Thank you. Questions?
One question. So, do you directly encode, block encode the square root? And if so, like, does the block encoding become simpler because you're like block encoding a quadratic Hamiltonian instead of like a quartic one in the square root?
That's a good question. So this would sort of look like we would have to have access to this HSA thing, which would like be accessing this square root. But in a lot of these algorithms, you can show that this particular representation is not necessary. You're just given access. If you're just given access to the A's, then you can. This is like a rectangular block encoding, so it's like tall and thin, right? This is just sort of the Hermitianized version. You can take each of your SOS operators and just make each of these A's like a long column or a big row, and then it's the same. But it's usually more expensive because this SOS representation, to have a good lower bound, has to be pretty complicated. It has to approximately annihilate your ground state.
Thank you.
Hi, I was curious, in the first quantized examples you showed, you said you had an analytical expression for the sum of squares decomposition?
Yeah.
I was wondering how you were able to back out what the SOS energy was, I guess the energy lower bound that you get from that expression?
Oh, yeah. So there's a way to bound this in a very loose way that gives you a lower bound that does not give you a speed up. But that sort of violates what we know about how energy should scale for a given chunk of matter. And so you can sort of argue from a physical argument about the arrangement of atoms and what their extensive energy should be. It's sort of like an Ewald argument that this should be the scaling of the lower bound. And that's sufficient to give you a speed up. And in this case, like we did a bunch of numerics to verify that's the case.
One more question.
So I'm curious about so there's the one slide which compares the Toffoli gates of different methods.
This like translation table?
No, like there's a graph which number of Toffoli gates. This one, yeah.
Oh yeah.
So I'm curious about how do you estimate this value? So in particular, my overall impression is So I think this spectral amplification based on quantum singular value transformation, right?
I mean, you can put it in with, you can combine it with QSVT if you want, but they're sort of separate things.
Yeah. So so my question is how do you estimate Toffoli? So for example, if you were using QSVT or other methods, there will be, sub steps of preparing result states and whatever. Do you count those things?
In a very detailed, excruciating way, yes. You compile it in your mind, and then you write it all down, and you test it with Qualtran. You simulate little pieces of it to try to make it sure it's correct.
Okay.
Yes.
Thank you.
All right, let's thank Nick one more time.